So let's change up our gears a little bit and let's talk about the non-parametric Kruskal-Wallis test and a little something else I'm sneaking in called the Dunn test. So just to kind of give our flash recap back again, the advantages of doing non-parametric testing is that the parametrics are worried about the dispersion and the shape of the variables that you're working with. Non-parametrics aren't concerned about these things. They deal with medians and IQRs and non-parametric ranges that don't have to worry about the shape of the data. Now the parametric tests that we're dealing with, we have a lot of these assumptions and dealing with the violations can cause us to have inaccurate results. So the non-parametric version has an advantage that they're a bit easier on the calculations, and because they don't have these sorts of assumptions, we're not going to be worried about the inaccuracy of our results based on any violations. Now, of course, with some advantages are going to come some cons and disadvantages. First of all, they tend to be less powerful. Parametric tests are always more powerful in terms of their analysis. Power then meaning it converts directly into power analyses to help find higher levels of power. It also then helps us become more sure about where these exact differences occur. Having rank differences compared to exact numerical values, you're losing that sort of granularity that you can get. Now, a slight disadvantage here that when you're doing these non-parametric tests, and specifically the Kruskal-Wallis test, is you're going to need a higher sample size compared to what you're dealing with the non-parametrics, okay? Generally speaking, you're going to need to have, on orders of magnitude, a large handful size. I tend to have at least 10 to 15 samples per group that you're doing these comparison observations on. 20 is definitely a good buffer, okay? So for each sample size group, 10 to 15 at a minimum for non-parametrics, 20 is a good buffer. Of course, with some of the data sets we're working on, you're going to have far more than that. But if you were to apply this to like the Munchkin data that we were working on, we'd be in kind of trouble. We wouldn't have a large enough sample size to want to have non-parametric testing for that. So is non-parametric the way? Is this going to be the solution because it's easier to calculate and it deals with some of these differences? Well, I said before that ANOVA is robust to many of these violations, things like normality and outliers and variance and some of these different things. And so we can go ahead and slip on some of these different assumptions, and the one-way ANOVA is still going to pull through for us. It's still going to work pretty well. But it relies on having equal sample sizes for our different groups. The more deviation we have towards these unequal sample sizes, the more differences there are in these sample sizes, the less robust the one-way ANOVA is going to be for us. Okay, so when you've got only one violation, you're all right. If you've got two violations, all right, you could still be on the fence. If you have equal sample sizes, you should be all right. But once you start getting to the unequal, and your threshold for unequal can be as many as twice as large. And in order to determine if you have unequal sample sizes, twice as large as the smallest group to the largest group is usually a good rule of thumb, okay? Smallest to largest, twice as large, or half the size, depending which way you're doing your calculations. Now, of course, when you start working with larger and larger sample groups, the spreads between those are going to be different, so it's sort of a soft rule here. Now, we also need to consider your independence assumption. That's something that underlies most of the statistical tests that we're working on. And so if you are violating an independence assumption, then we just need to worry about, is ANOVA going to be the best fit at all? And to be transparent about the potential biases you might have in your research. The independence assumption is aside from making our decision if we're going to do a non-parametric test or not. So now that we're good on most of those, we can figure out if the variance violation specifically, how does that work with this? Well, with the variance violation, you're doing the Levine's test, and you can center it at the mean to do the non-parametric version of it. That's going to give you the Brown-Forsyth. I said you didn't have to worry about the name, but if you're doing the non-parametric version and you violate your variance on that, then you're going to go ahead and use the Welch's ANOVA like I just showed you a few minutes ago. Now, if you violate normality, right, and you're worried about it, then we can go ahead and worry about the Kruskal-Wallis test. Normality is the one that we're really talking about, the shape of the data and how it's being dispersed across. So when we do that, we can switch into the non-parametric with the Kruskal-Wallis. Let's talk more specifically about it. It is similar to the Mann-Whitney U and the Wilcoxon rank sum that you learned about with your t-tests. It's going to take your interval ratio numeric data, and it's going to convert it to ranks. And once it's converted to ranks, the Kruskal-Wallis is going to look at the difference in mean ranks compared to each other rather than mean exact values that we have there. Of course, we still need to have an independent variable with 3 or more categories. And once we have that, we can go ahead and just plug and play from there. We don't have to worry about normality. And just as a side note, if you have unequal variance issues, the Kruskal-Wallis is not going to fix that one for you, okay? And if you violate both with normality and unequal variances, you're just going to have to kind of weigh the scales and figure out which one is the more important violation that you need to get concerned about. Because Welch doesn't fix ANOVA, and Kruskal-Wallis Welch doesn't fix normality, and Kruskal-Wallis doesn't fix unequal variances, so there's a trade-off at play. Now I'm going to show you a brief example here of the Kruskal-Wallis in action. We're using data from the General Social Survey 2016, and we have a religion variable that has all sorts of different religions. And I've recoded it, so I'm only looking at 5 different religions. The code for it is in the accompanying script file if you want to see how I did the recoding for that. And we are using it on a dependent variable of prayer. Prayer is asking, how much do you happen to pray when you go to church and things like this? And it goes from a value of 1, which is sort of like more than once a day. Value 2 is sort of once a day, and then weekly and every so often, and all the way up to a highest value of 6, which is never. So it's an ordinal measure, and it has 6 different levels to it. So it qualifies for us to hit our minimum number we need for the Kruskal-Wallis, for the use as a numeric type of variable. And we're going to plug it in the Kruskal-Wallis because as ordinal, it already meets the specifications that we can go ahead and use it for a Kruskal-Wallis, even though we have the option to use it in the one-way ANOVA here. Now, as I had said before in some of these previous things here, that the Kruskal-Wallis, when we're working with it, it's going to generate our analysis out. It's going to say it's a Kruskal-Wallis rank sum test. It's going to tell the variables up in the data. Now, funny thing to note is that the Kruskal-Wallis gives you a chi-square value, and with a single degree of freedom and a p-value. Do not be fooled by the chi-square value here, okay? It's actually generating for you an h. Totally confusing. I know, I get it. I didn't write the rules on this one, nor did I write the R code for it, so just kind of go with me on this. You're going to report the Kruskal-Wallis as an H statistic with your degree of freedom, the 1 degree of freedom that you're going to get in there, equal to your Kruskal-Wallis value, and then report your p-value, and you're good to go. Okay? So just keep these things in mind, that even though it says chi-square, we're going to use the H value. And the greater differences you have in your group shapes, the Kruskal-Wallis might become more inaccurate. So it's going to be robust against normality only up into a point. And that unequal variance in the shapes are where we're getting this here. And you specify the Kruskal-Wallis as the Kruskal.test d tilde IV, just like you would do for your one-way ANOVA and whatnot. Now with the Kruskal-Wallis test, we do have a post hoc that can go along with it. We had 2-key HSD for our one-way ANOVA, and when you did the one-way ANOVA with the Welch version, we used the pairwise.t.test with the Bonferroni as sort of our filler in between. But with the non-parametric version, we're going to use something called the Dunn test. And the Dunn test, you're going to need to install the Desk Tools package, and we use the Dunn test, capital D, capital T in test, DV, comma, IV, comma, method equals Bonferroni. So we're going to still use the Bonferroni correction like we did with the pairwise.t.test, which remember is more conservative than the 2-key. And we're going to go ahead and plug that in here, and we can run that, and it's going to give us a pairwise differentiation by the mean rank sum. So in this case, we're going to use our religion variable on prayer, and so we have the Dunn test on our prayer variable, comma, religion, method equals Bonferroni. Now that we've got the Dunn test run here, and we're looking at an action, what you see going down the side here looks very similar to the 2-key test, where we have the pairs identified in the first column, then followed by a mean rank difference of those pairs in the second column, and then a p-value of those differences in the third. Now keep in mind here that prayer was ranked where 1 was praying the most and 6 was praying the least. So as numbers got higher up in their ranking differences, they were less likely to be praying. Now, when it said Hindus minus Catholics, we had a mean rank difference of 167 with a p-value of 0.86. If we were to use our traditional alpha of 0.05, we would see this as a non-statistically significant difference. So there's really no difference between Hindus and Catholics in the amount of prayer ranks that they have. Let's look at the next one, though, where we have Jews and Catholics, and there we have a mean rank difference of 2.28 and a p-value of very small. It's got the scientific notation on it. So we see that there is indeed a mean rank difference, and typically when we're looking at these mean ranks here and the differences between them, the first value, if it's higher, subtracting from the second group, will give you a positive mean ranking difference. Whereas if you have a negative value, it means the second group had the higher value. Now, that should be pretty straightforward, but because our coding here was such that the high number was less prayer, it actually has the flip side here than when we're looking in these values here, that Jews had a higher number ranking than Catholics, but that higher number ranking meant praying less than a lower number. So it would be that Catholics pray more than Jews in this particular regard. I'm going to go ahead and filter out those results here visually of those that were not statistically significant and see if we can identify any patterns from those that weren't or those that were significant and what some of those differences are here. So those that stand out show that Jews and Catholics were significant, none in Catholics were significant, Muslims and Jews, none in Muslims. So those are sort of some of these metrics here, but I'm not really seeing anything that stands out and pops up right away. Catholics prayed more than Jews. Catholics prayed more those who did not identify with religion. Jews prayed less than Muslims. Muslims pray more than Jews. And Muslims pray more than those who are non-religious. So in that particular regard, no religious identity often prayed less, which makes sense if we're looking at a prayer variable. And Catholics and Muslims prayed more than Jews or those that didn't, which kind of stands to our general guesses about the world, but I wouldn't take that to too much heart here because we didn't see any strong patterns with some of the other religions as well and how these go out. So when you look at these, really just try to see if there's a story to tell and how we can parse some of that out. All right. So with that, that kind of wraps up this video here, and I'll see you all in our next video where we have another example on doing these in R, and we're going to apply some of the tests that we used just here, and then the last one on effect sizes and power. I'll see you then.